Next, we're going to take on corollary 4.34. If t is an operator on H, then t is positive if and only if there exists an operator S on H such that t is equal to the adjunct of S times S. Now, going in one direction, it's obvious because of proposition 4.14, which tells us that S star S is positive. So if it's equal to t, then t is positive. Going back the other way, it's also relatively easy because we can take S to equal the square root of t. And you'll note that the square root of t is a positive function by corollary 2.37. Else 2.37, and it is self-adjoining by corollary 4.32. So, following that, the book goes in, so that gives us a result. And following that, the book goes into a brief discussion on the complex numbers in the fact that all of them can be written as a product of a unit vector and a non-zero positive real number. That is, except for 0. If you remove 0 from the complex plane, you get this nice way to factor them, which is vaguely reminiscent of polar coordinates, if not identical to them in a sense. And they go on to say that this concept holds when you transfer over to operators in Cn, where instead of the factoring being a unit vector and a positive number, you have a positive operator and a unitary operator. Lastly, the book goes on to then note that we're going to eventually prove a result for operators on arbitrary Hilbert spaces, although you need several corollaries built up before you can, several requirements before that theorem can hold. So moving on to definition 4.35, an operator V on a Hilbert space H is a partial isometry if VF, the norm of VF is equal to F for all F in the orthogonal complement of the kernel V. So in other words, it is an isometry on the orthogonal complement of V. The book then notes that in the case when the kernel equals 0, you obviously have just that V is an isometry, so these definitions line up nicely when the kernel is trivial. We then give a name to the orthogonal complement of the kernel of V, which we call the initial space, and note that it is always closed. Now, next, the book has a brief commentary on the fact that in finite dimensions, every isometry is a unitary operator. However, in arbitrary Hilbert spaces, this is no longer the case. So, moving on to our next portion, we're going to have an example, which is 4.36, and it's going to be working in L2. Specifically, what we're going to show is that there exists an isometry operator on L2 that is not a unitary operator. So to define this guy, we're going to call him U plus, and it is going to be defined as U plus of F of n. So F being an element of L2 Z plus is equal to F of n minus 1 when n is greater than 0 and 0 else. So what this is basically doing is just shifting it over 1, and the book notes that this particular operator is called a unilateral shift. Now we note that if you take a sum that converges from I equals 1 to infinity of a sub n, this is equal to 0 plus the sum I equals 2 to infinity of a sub n minus 1, which implies that U plus is an isometry. And I apologize, these should be squared. Yes. So what we now have is that if you basically the operator shifts everything over one, so we can pull the 0 out in the front of the sum without causing any problems with the norm itself. Now, to show that u plus is not unitary, we need to find u star, u plus star, which we note is, it turns out, equal to this. And plus 1. And the reason we know this is because the sum from I equals 2 to infinity of a sub I minus 1 bi conjugate is equal to the sum I equals 1 to infinity of ai bi plus 1 conjugate. And again, this is just by reindexing. But this gives us, in fact, that this is our adjunct for u plus. Now, what we note is that if we have a sequence a sub n that is in our space L2z plus, and such that a1 does not equal 0, then u plus star of a sub n is equal to the sequence 0, a2, a3, and so on, which is not the same thing as a sub n, because they have a different first term. So then automatically we get that u plus is not a unitary operator.